we have all the building blocks to look at what is a linear system and how can we solve it. A linear system is a multiplication between a matrix, an unknown vector, and we know that this product is equal to a known vector. The usual formulation is AX equal to B. We want A to be a square matrix, otherwise it doesn't have an inverse. And we want the sizes to be correct, so we want A to be size n times n and B to be size n. So what we know is that there is a transformation that go from Rn to Rn that we call A. We have a vector B at the end of this transformation, and we want to go back. And we want to find x such that Ax is equal to B. That means that Ax is A inverse times B. So let's look for an example. Ax equal to B. A is a 2 by 2 matrix with 1 in the first element and 0 everywhere else. And B is equal to 3, 0. So the determinant of A, you can do it very simply. It's 1 times the determinant of 0, so it's 0. So the inverse does not exist. If we want to solve this equation, well, we notice that A times a vector x with values x1 and x2 is equal to the vector x1 and 0. If we want to place that equal to 3, it means that any vector that has 3 as a first element and whatever else in the second element is a solution to our linear system. So we have infinitely many solutions. The determinant of A is equal to 0, therefore the inverse does not exist, therefore we have problems solving this linear system. On the other hand, if B was set to be 1, 1, there is no solution, there is no x such that A multiplied by x can give you something that is not 0 in the second value. So this is why determinants are important. Determinants allow you to determine if there is or not a solution to your linear system. If there is a unique solution, only if the determinant is non-zero. It's just a computational way of determining it. So if we have something more interesting, so we have A is equal to 1, 2, 3, 4, and B is any vector, B1 and B2. Then the determinant of A is 1 multiplied by 4 minus 3 multiplied by the determinant of 2. Where does the minus come from? I want you to check out the formula and figure out why I have a minus in there. The determinant of 4 is 4, the determinant of 2 is 2, so here we can compute it. The determinant of A is minus 2. The only thing we want is for it to be not equal to 0. So we don't care if it's positive or negative, it's minus 2. So A inverse exists. How can we compute A inverse? There is a process called Gaussian elimination. It's the most common way to find the inverse. And it works by saying that you have a matrix in a squared matrix n by n, and you write that matrix followed with a line in between by the identity. And if you call each row of this new extended matrix Cj, we are allowed to make a couple of steps. First, we can exchange two rows. Then we can replace a row by itself plus a scalar multiplication of any other row. Or we can replace a row by a scalar multiplication of itself, assuming you're multiplying by something that is not 0. And what is the goal of all this? Through these three steps, we want to go from the matrix that we just wrote, that is A and the identity. We want to go to the identity and something on the right. And that something on the right happens to be the inverse of A. So let's continue the example we had before. We had the matrix 1, 2, 3, 4. And we want to find the inverse of this matrix. So we write A and the identity. So you have 1, 2, 3, 4 on one side, and then a vertical bar and the identity on the right. 1, 0, 0, 1. through some steps, we want to have the identity on the left instead of on the right. And we can only do the 3 steps we just said. So as first step, I'd like to get rid of the 3 at the bottom left corner of A. So I take the second line, C2, and I replace it by C2 minus 3C1. This makes it in such a way that the first element of C2 disappears, because now we have 3 minus 3 times 1. So look at the first row is exactly the same as before. The only thing we have changed is the second row. The second row now has itself minus 3 times the first row. So we have 3 minus 3 times 1, 4 minus 3 times 2, where 2 is the second element of the first row, 0 minus 3 times 1, where 1 comes from the previous row, and 1 minus 3 times 0. So we have succeeded in getting rid of the left bottom corner. Now we have in the left of our bar 1, 2, 0, and minus 2. And on the right, we have changed things around. It's not the identity anymore. It's 1, 0, minus 3, 1. So we rewrite things, and we want to get the identity on the left. So what we want to do is change that minus 2, that is on the diagonal of our matrix on the left, with a 1. So we replace the second line by itself multiplied by minus 1/2. So this gives us neatly 1 on the diagonal of the left matrix. And all the other terms in that line get changed. So now instead of 0 minus 2 minus 3, 1, we have 0, 1, 3/2 minus 1/2. So now we're quite close to finishing, but we want the left side to be the identity. So the last thing we need is to transform the top right corner, the 2, into a 0. So how we do that is to replace the first line by the first line minus twice the second line. So now we have the second line stays the same, and the first line gets changed into 1, 2 plus minus 2 times 1, where minus 2 is what we chose as a scalar multiplication, and 1 comes from the bottom line. Then we have 1 minus 2 times 3 divided by 2, and the last element is 0, what we had before, plus 2 multiplied by 1/2. So this simplifies away, and we have 1, 0, 0, 1 on the left of our bar, and on the right we have minus 2, 1, 3/2, and minus 1/2. And that is the inverse of our matrix A. So it holds that for any square matrix, if it is invertible, so if it has an inverse, then A multiplied by its inverse is equal to the identity. Also, the inverse multiplied by A is equal to the same identity. So we can check this out. We have built A, we have built the inverse of A. Let's multiply these two things and see if we retrieve the identity. Otherwise, we must have done something wrong in the calculations. So here we go. We take the first row of A and the first column of A at the minus 1, and we solve this. Then the first row of A and the second column of A minus 1. And we go on. The second row of A times the first column of A at the minus 1, and the second row times the second column. And this is indeed the identity. I leave A at the minus 1 times A as an exercise. Now that we have A inverse, we can compute X as X equals A inverse times B. So let's continue solving linear systems. We have A matrix 2 by 2, a vector B, and we want to find X such that AX is equal to B. And we know by what we have talked about until now that X is A inverse times B. Sometimes A inverse is slow to compute. So there are some ways to make it slightly faster. Instead of solving A bar I, with I being the inverse, we write A bar B. So instead of having the square inverse on the side, we only have the B vector. And with the same restrictions as before, we have the goal of transforming A into I. And once we do that, on the right side of the power bar, instead of having B, we'll have X. So let's try to work this out. We have A, that is the matrix 1, 2, 3, 5. B is the vector 1, 0. And we write A bar B. So it's just a bigger matrix with 1, 2, 3, 5 on the left and 1, 0 on the right. And we want to transform the first block of this matrix into the identity. So we take the second row and we want to cancel the first element of that row. So we want to subtract 3 to that first element, and we can subtract 3 by multiplying the first row by -3 and summing them up. So we replace the second row by C2 minus 3C1, and that gives us 0 on the first element. But it also gives us -1 on the second element. So we're going to multiply the second row by -1 in order to get rid of that minus in front of the 1. So now we have 1, 2, 0, 1. We are aiming to get the identity, so we're going to get rid of that 2 in the corner. And through all that, we keep track of what is happening on the right of our bar, but we don't really care until the very last step. So we take a new step, we replace the first row by itself minus twice the second row. And this indeed cancels out our off-diagonal element. Now we have on the left 1, 0, 0, 1, and by keeping track of what is happening, we have -5, 3 on the left, on the right, sorry. So we have the solution that is -5, 3. Let's check that A times X is indeed equal to B. So we multiplied the matrix 1, 2, 3, 5 to the vector that we just built, that is -5 divided by 3. So first row of A times X gives us -5 plus 2 times 3. And second row of A multiplied by X, and that indeed gives us 1 in the first element and 0 in the second. So we have retrieved B, we have successfully solved our linear system. A subcategory of linear systems is called homogeneous. We have already seen homogeneous equations multiple times, and homogeneous linear systems are not that different. Ax equal to b is homogeneous if b is equal to 0. But now you have to remember that b is a vector, so it's a 0 vector. If A is invertible, so it has an inverse, the only solution to a homogeneous linear system is x equal to 0. Why? Because, well, if there is only one solution, well, if A is invertible, then there is only one solution, and that solution must be such that you have only zeros as output, so x needs to be equal to 0. If, and only if, there exists A different than 0, such that Ax is equal to 0, with A squared, then A is not invertible.